Very good. Well, good morning. I'm Ted Chandler. I am co-founder and managing director of NRV. We invest in promising early stage businesses, predominantly in the Commonwealth of Virginia. But more pertinently to this meeting, I'm very pleased and honored to be co-founder and co-chair of RVA757 Connects. So on behalf of my co-founder, Tom Frantz, who is really the godfather of this initiative, we welcome y'all to this innovation series. So Laura, are you going to be running this or will I? Yes, good. Okay, here's our agenda. I'm going to give you a very quick update on RVA 757, introduce Stuart Henderson, our featured speaker, and then Stuart is going to present an overview of Jefferson Lab's plans for supercomputing. We'll have a Q&A section and briefly what's next. So 2 important session notes. We are recording this. So this presentation will have legs. It will be on our website and there'll be an opportunity for each of us to revisit it if we wish, but also where you think the content here would be beneficial to some of your colleagues or friends, please let them know about its availability. Also, we're going to have a Q&A on this, and we ask that you use the chat box, send the questions to Laura, and she will run the Q&A at the end of it. Go. Okay, our mission. Improve the economic success and quality of life for everyone in the RVA and 757 regions. Wow, is that broad or what? Of course it is. It's broad because we've broadened our geography. It's broad because we only are going to be working on those kinds of initiatives that will make a very big difference when successful. And we have a broad array of businesses and municipalities that are working hand in hand to get this done. Next. So our priority focus areas, I'm not going to cover these. You can just glance at them. These are our priorities for the year. I do want to update you on the I-64 gap situation. So we have had this as a priority for the last 2 years. As y'all know, if you travel 64 at all, there's been tremendous expansion of 64 over the last few years. Unfortunately, there is one gap, 29 miles, that fell to the back burner, and it seemed as if there was not going to be sufficient attention to this. We've been working on this. We began last year. We've been advocating for it, making connections, and the real stars here are the planning district councils from each of our geographies that have also been putting in some advocacy with respect to this. At the moment, we've got some funding on it. We've got some momentum. There's some infrastructure money coming, and we are working directly with the Virginia Department of Transportation on these grant applications. I want to do a shout out to the Go Virginia programs, and in both the 4th and 5th districts, which is what our geography covers, because of that study, we're able to give data-based advocacy to VDOT as we work forward to getting this done. Next. What you can do is if you have contacts in the state level, elected officials, cabinet levels, et cetera, your individual advocacy of you and your business would be helpful. If you'd like kind of specific bullet points as to how to do that, contact Laura. Next. Advancing our mega regions brand. Next. We're very pleased to say that we have hired as our communications director for RVA 757, Greg Gilligan. If you're from the RVA area, you know that he has served as the business editor of the Richmond Times-Dispatch for quite some time. He has 30 years in the newspaper business. He will be joining us full time. This is an important step for this collaborative. In any collaboration, communications is the currency of the realm, and he will bring in great capabilities to help us get the message out and help all of us identify the innovative innovations that are going on throughout our geography. Next. Okay, today's speaker. Very pleased to have Stuart Henderson. You can turn to the next page. This is Stuart's resume. If I actually gave appropriate credit to Stuart for all he has accomplished, he would eat very much into his speaking time. So what I will say is that he has been the director of Jefferson Lab since 2017. Jefferson Lab, as you will very quickly learn, is a world-class research facility. You know, we throw world-class around like nothing. Well, literally world-class, and not many organizations of this type in the world. His influence is not only running this, this laboratory, but also the role that he plays on our national energy policy by serving on various of the Department of Energy advisory boards. So we're very, very pleased to have Stuart here presenting. And with that introduction, I turn it over to Stuart.
Thanks very much, Ted. Thanks so much for the introduction. Thanks very much, Laura. Really appreciate it. I'm going to share my screen. Hopefully this all just works. How's that? Can you see that? Great. Let me get a little pointer here. All right. Well, thanks so much. I really appreciate this opportunity to tell you all about our plans at Jefferson Lab for not only putting Virginia on the map with regards to supercomputing, but really putting Virginia at the center of the supercomputing universe. And where we couldn't be more excited about this, couldn't be more excited about the opportunity that is before the laboratory, before our region, and before the Commonwealth for a really significant asset that any state would be very fortunate to land, and that we're trying very hard to land here at Jefferson Lab. So the topic is supercomputing, and like I said, a very exciting initiative and opportunity right in front of us. But I want to start out a little bit with some of the context. So Jefferson Lab is a Department of Energy lab. What's the connection between the Department of Energy and supercomputing? What's the connection between Jefferson Lab and the Department of Energy? So this context is important. So I'm just going to spend one slide on some ancient history. So let me roll back the clock to 1945. World War II was coming to an end. You know, before that, there was not really a concept of government-supported scientific research at a large scale. It was really the Manhattan Project in World War II that brought that notion to the fore. And importantly, for what I want to describe, the events surrounding the end of World War II, where a very key advisor to President Roosevelt by the name of Vannevar Bush was charged with thinking through how this government-supported scientific enterprise that came together in the Manhattan Project could transition in the post-war era and lead to not only economic development, but jobs, national security, improvements in health and welfare of American citizens in the post-war era. So Vannevar Bush considered this and put together a very influential report called Science, the Endless Frontier, which basically laid out the game plan for government-sponsored research across universities, It called for the invention of the National Science Foundation, which of course happened. And it called for the invention of a complex of government-funded research laboratories whose sole purpose was to explore basic science at the frontiers of our knowledge. And today, that complex of government laboratories is the U.S. Department of Energy National Labs. So those labs that were part of the Manhattan Project, they weren't called labs then, they had other names, but those who were part of the Manhattan Project, Oak Ridge National Lab, Los Alamos are some of the famous ones. Another one up here outside of the Bay Area, very heavily involved. Those became sort of founding members of the U.S. Department of Energy National Lab complex. And that complex has grown since 1945 to encompass 17 U.S. Department of Energy National Labs, with Jefferson Lab right here on the peninsula and in Hampton Roads being the newest member of the set of 17 U.S. Department of Energy National Labs. So across this network of laboratories, there is no topic in science and technology in the physical sciences that is not covered across this complex. You name a physical science and a cutting edge technology or research topic, and it is covered and researched at one or more of these national labs. The labs, of course, also encompass a role that came out of the Manhattan Project mission for weapons. And, although Jefferson Lab has nothing to do with that part of the DOE, there are a set of national labs that focus on weapons and nuclear security. There are a set of national labs that focus on energy technologies, like the National Renewable Energy Laboratory in Colorado, like the Idaho National Laboratory that focuses on nuclear energy topics in Idaho. We're somewhat unique in the national lab system. We focus completely on basic fundamental research. We don't do applied energy technology research. We focus on basic fundamental science. So as I said, we're one of the DOE's 17 national labs. We were created in the 1980s and built in the mid 80s to mid 90s and formed to operate a very unique world-leading facility called the Continuous Electron Beam Accelerator Facility. It is an advanced particle accelerator that functions a little bit like an electron microscope for exploring the subatomic world, the interiors of protons and neutrons. We're literally trying to understand what is inside protons and neutrons and how do those subatomic constituents form all the matter in the universe. So science at its most basic and most fundamental. Because we're unique in the world, we attract a community of nuclear physicists from around the world that numbers about 1,600. They come from about 35 countries. They come from 38, I think, of the states in the US and from 35 countries around the world. They flock to Jefferson Lab to carry out experiments using this one-of-a-kind facility. And our mission really is exploring the very fundamental science of protons, neutrons, and the atomic nucleus using the Continuous Electron Beam Accelerator Facility, bringing in our capabilities in theory and our capabilities in supercomputing, which I'm going to say more about. Some basic numbers about the lab. We have 750 employees, an annual budget of about $160 million. We're located in Newport News. One of the numbers we're most proud of is 1/3 of the United States PhDs, doctorates in nuclear physics that are granted annually, carried out their research at Jefferson Lab. So we serve a very important educational role. We don't grant degrees, of course, but graduate students at Old Dominion University and William and Mary and Virginia Tech and UVA and 100 other academic institutions in the United States and another 50 academic institutions around the world send their students to Jefferson Lab to carry out their research that allows them to complete a doctorate. We also have a very significant footprint in local K through 12 STEM education. We serve as a real resource for Hampton Roads, given this very unique facility that we have, and exposing students who wouldn't otherwise have an opportunity to be exposed to really cutting edge science and technology. And we have an opportunity to bring them here and embed them in our programs. So we really explore matter at the most fundamental level. So let me give a quick kind of very short lesson on nuclear physics, and then I'm going to turn to supercomputing. So, what is matter? So you think of a leaf. What is a leaf made up of? Well, the molecule that makes a leaf do what it does, which is convert sunlight to energy, is a chlorophyll molecule. It has about 100 atoms in a very particular arrangement. You zero in on one of those atoms, and this is kind of our cartoon picture of an atom. There are electrons. Those electrons sort of orbit a atomic nucleus. The nucleus itself is made up of protons and neutrons, and this is nowhere near to scale. At the scale of the electrons, you wouldn't see an atomic nucleus. It's a tiny little dot. It's about 100,000 times smaller than this cloud of electrons. So, in the middle of this cloud of electrons is a very teeny tiny atomic nucleus. And that's what we're trying to study. We're trying to understand what makes the atomic nucleus tick at its most basic level. So we know protons and neutrons come together to form the atomic nucleus and form all the elements that make up our world. An individual proton or neutron is teeny tiny. It is 1/1,000,000th of a billionth of a meter in size. And using our particle accelerator, we shoot beams of electrons into the middle of these protons and neutrons to see what's in there. And what we know is in there are subatomic particles that are called quarks. We now know that these subatomic particles come together in very special arrangements, and they're governed by the strongest known force in the universe that binds these quarks together into individual protons and neutrons. And we're trying to understand matter, how it works at absolutely the most basic and fundamental level of the subatomic particles that make up you and me and all of the matter that is around us and all of the matter that we see. So that's what we're about as a lab. To carry this out, though, we need supercomputers. We need supercomputers to explore this complicated theory, and we need supercomputers to analyze the data. And that's kind of the launching point for this very exciting initiative in supercomputing that stands to, as I said, make Virginia one of the key places on the planet for supercomputing at a massive scale, with a particular focus on data analytics. So with that, let me segue into supercomputing. What is it? Why do we need it? What do we do with supercomputers? What do I even mean by that word? So first off, a picture. Here's a picture of a supercomputer. This is the fastest supercomputer in the United States. It is called Summit. Its components were built by IBM and NVIDIA. It's located at the U.S. Department of Energy's Oak Ridge National Lab. So that was one of those 17 labs that I pointed out on that map of the United States earlier. This has a speed. So supercomputers, their performance is measured in terms of their speed in carrying out calculations. And that goes by a very funny sort of unit of measure called a flop. FLOP stands for floating point operation. You can think of that as one calculation. So if you get out a pencil and a piece of paper, and I ask you to do some long division and take the number 127.3 and divide into that the number 11.79, and you grind away, that might take you 2 minutes to do that. You've just carried out one floating point operation and it took you 2 minutes to do that. If you punch those numbers in on your calculator, it might take you, 5 seconds to do that. Well, this supercomputer can do 200,000 trillion of those calculations per second. So that's a mind-bogglingly large number. It's hard to wrap your head around that. Picture a trillion. A trillion is a 1,000 billion. And then picture 200,000 of those 1,000 billions. And that's what we're talking about. So it's an enormous number. I'll show a chart in a moment showing how this, speed has grown over time. So this supercomputer is made up of about 4,700 so-called nodes. This is one of the nodes. Inside each of those are 2 CPUs. Your computer, your laptop, or your desktop probably has 1 CPU. It might have 2 CPUs. These are very special CPUs. They themselves have 22 processors in them. So each of those processors is an individual computer. Along with that are a set of NVIDIA so-called graphical processing units. These are special types of computers. So each one of these nodes contains a bunch of computers and processors themselves. You add all this up, this is a supercomputer that has 2.4 million individual pieces of electronics in there that can make a calculation. And these 2.4 million individual little computers all work in tandem, all work together. They take 10 megawatts of power to drive this and carry out calculations at the largest scale. So you ask, where are the supercomputers in the world? And where are the top ones? So let me explain this complicated chart in a second. But first, let me tell you where the top dozen supercomputers are in the world. Number 1 is in Japan. It's this machine called supercomputer Fugaku. Number 2 is the picture I just showed you. It's at Oak Ridge National Lab, again, U.S. Department of Energy National Lab. Number 3 is at another U.S. DOE National Lab, Lawrence Livermore National Lab. It's called Sierra. Number 4 is in China. Number 5 is at another U.S. DOE National Lab in the Bay Area called the Lawrence Berkeley National Lab. That's called Perlmutter. Number 6 is at NVIDIA Corporation. 7's in China, 8's in Germany, 9's in Italy. Number 10 is at Microsoft. Number 11's in South Korea. Number 12 is at Argonne National Lab, another US DOE National Lab. So you count up 1, 2, 3, 4 of the world's top dozen supercomputers are at United States Department of Energy National Lab. So this is a very key part of the DOE mission, is building and operating the world's fastest supercomputers, for most cases, for open, basic, fundamental scientific research. That's what number 2 does. That's what number 5 does. That's what number 6 does. Number 3 is a little special. It's contained at one of the National Nuclear Security Administration labs. It does classified work. The others do basic open science for academia, for other national labs, and for industry, very importantly. So DOE, like I said, has a fundamental role in supercomputing, and they are really the nation's key steward for the top end of supercomputing in the United States, both for open science and for national security. Okay, this is a complicated but really fascinating map of the top 500 supercomputers. So in this list, you can go online and find this. These top 500 are all listed there, and they're shown broken out by those located in the United States, those located in Japan, those located in China. So this is a map by country: Germany, Netherlands, South Korea, Italy. If you're following my little pointer, France, the UK is somewhere over here. There's Russia, Canada. So the US is the major player. And the size of these boxes is the speed of the supercomputer. So the Japanese supercomputer is number 1. That's this one. The one at Oak Ridge is number 2. That's this one. You know, China comes in with this one at number 4. So it's a really interesting, diagram of speed and number of supercomputers throughout the world. The Jefferson Lab supercomputer will feature prominently on this diagram when we're successful in attracting it, building it, bringing it to Jefferson Lab. So, what I just described is a story that has taken a century to build out. It started with the invention of the transistor and the initial patents for a transistor by a scientist named Lilienfeld. Bell Labs developed the transistor, and these three gentlemen won the Nobel Prize in Physics in the mid-1950s for the first demonstration of a transistor. Robert Noyce, who founded Fairchild Semiconductor and Intel, was the first to bring individual transistors together into what today we would call an integrated circuit or a microchip. You've probably heard about Moore's law. That is a law that says that the number of transistors one can locate on a microchip doubles every 2 years. And that has been the case since the founding of Fairchild and Intel. And you see, if you can read these little dots, this first dot is an Intel microprocessor. Up until the present, this is a growth in doubling the number of transistors on a microchip about every 2 years. And some of the way stations along the way, the personal computer back in the early, late 1980s, had about 200,000 transistors. One of the original ones had about 2,000, so 200,000, a couple decades later. Well, now your iPhone, has got about 12 billion transistors on it. And, your iPhone is up here, and it was just a few decades ago that, we were operating down here. The cost of this 200,000 transistor, what now would be a laughably slow computer, was $15,000 today. And now we're operating up here where that iPhone is about $1,000. So it's this incredible growth in Moore's law in the ability to cram transistors and therefore computing power into small areas that has driven this incredible increase, incredible performance of supercomputing over time. So this shows since 1990, the growth in supercomputing speed. If you focus on this sort of brown, this is the top supercomputer in the world on any given year, and the growth in its capabilities. So back here in 1990, we were measuring things in the millions of flops, millions of calculations per second. We then entered billions of calculations per second. That's gigaflop. Teraflop is thousands of billions of calculations per second. We then entered the 100,000 billion. I don't know. I'm losing myself in this, but each one of these is another factor of 10 going up. And today we talk about exaflops. So this growth has followed this trend that you see in this plot of Moore's law, we call it. So where's all this computing power going? What's it put to use for? So I'm going to start out first with some basic science and then move into some industry applications. So basic science, at Jefferson Lab, we're a nuclear physics lab. We want to understand how the nucleus works. We want to understand how the elements came into being. The elements around us, and by elements, I'm talking about, the nickel, tin, silicon, nitrogen, carbon, the elements that make up the earth and the earth's crust. And some of those elements are very valuable, and we have mining operations to mine them and extract them and put them to use. Those elements all had to be created somewhere. Most of those elements were created from the explosion of stars at the end of their life cycle out there somewhere in the universe. So we're all made up of stardust as a result of that. That's where all the elements came from. So we try to model from basic science what a supernova looks like, how the elements are generated through nuclear reactions as a star collapses and explodes in some of the most powerful, astronomical events in the universe. So we can do that on supercomputers and get a glimpse into how that works. You know, a little bit closer to home, the most sophisticated climate models that are hard at work now looking at climate change, you know, the assessments that come out have to come from very sophisticated models. The Intergovernmental Panel on Climate Change relies on these models, relies on supercomputers to run these very sophisticated models that are incredibly complex. They couple the physics of the ocean with the physics on the land and cloud formation and CO2 generation and you know, human population. They're incredibly sophisticated, and those require this massive computation at an absolutely massive scale. This is an example very close to home. This is simulating the evolution of the Chesapeake Bay. And this came out of some work done from William and Mary scientists using supercomputer resources to try and look at various aspects of health of the Chesapeake Bay. But more and more, supercomputing is foundational to modern life. There are many examples that have come out of COVID over the last few years. Oak Ridge National Lab supercomputing team taking a look at the level of individual proteins and protein structures, at how the virus is working and how vaccines interrupt the virus in terms of the interaction with the immune system and the potential for developing therapies for COVID. NVIDIA, a computer hardware vendor, has launched two initiatives. Both of these very recent. NVIDIA is working with drug companies in Europe, GlaxoSmithKline and AstraZeneca, to construct the UK's fastest supercomputer. And the reason that those companies are investing is to deploy artificial intelligence on their massive data sets that they have on protein structure, to try to teach a computer to search for candidate drugs for various diseases. So an incredibly exciting use of artificial intelligence and supercomputing that relies on massive data sets that these drug companies have. NVIDIA also is partnering with another company, again, for computational drug discovery, to look and evaluate billions of potential molecules for their use in therapeutics. There are many other examples, you know, very close to industrial needs. Here's a supercomputer redesign of airplane wings, turning a supercomputer and artificial intelligence algorithms loose on an optimal design from an aerodynamic point of view of airplane wings. Here's doing the same sort of thing with nuclear reactor technology, turning a supercomputer and artificial intelligence loose on optimizing, in this case, heat transfer to get the most heat and put the most heat to use in electrical generation in a next generation reactor. Here's an example from the wind turbine and wind energy industry of simulating airflow in a large wind farm, and how that airflow interacts the efficiency of extracting wind power from the wind flow itself. So here's sort of a cartoon of the distortion in the flow of wind as it makes a turbine turn. And that's important in designing a properly optimized wind farm. Here's another example down here where Oak Ridge National Lab partnered with the Department of Veterans Affairs to mine the massive health records that VA has to try and understand how those health records can really impact health and healthcare outcomes of our veterans. So, you know, the examples really are legion just across across the broad range from basic science to industrial applications to public health. Stored data is the other piece of this. So it's not only supercomputing, but what about the incredible growth in data, and what are we going to do with all that data? So this is an analysis that came out of something called the IDC Global Data Sphere a couple years ago. They tried to project the growth in stored and new data. So this is stored data. This is their projection from 2018 onward. And, you know, in these crazy units called zettabytes, 2018 was up here at about 1.5, and they're projecting that annually to triple, you know, over the next several years. These are different types of data platforms: hard disk drives, solid disk drives, non-volatile memory, you know, optical means DVD type storage, and physical tape, and so on. So what's going to happen with all that data? Everything I just described is producing more and more data. Where's it going to go? What's it used for? That is where Jefferson Lab comes in. So we put together a vision to the Department of Energy to build a supercomputer coupled with a data center, coupled with a suite of artificial intelligence tools, purpose-built for data analytics. So we want this facility to meet both of these needs of supercomputers being brought to bear for basic research and industrial applications, this incredible growth in data that is emerging both from basic science and industrial applications, and build a platform that brings all that together and does it in real time. So we put together a concept for something called the High Performance Data Facility that focuses on real-time analysis of big data, where real time means literally real time, in the sense of an experiment maybe running at another national lab that needs to analyze data immediately in order to steer that experiment in real time. Or that could be the electrical grid, simulating the electrical grid in response to a failure or environmental crisis or weather situation in real time, and immediately return analyses that are useful in real time. So that's what we've proposed. This is going to bring a world-leading and world-unique asset to Virginia. It's going to diversify Jefferson Lab's scientific mission, and it's going to open up, certainly for Jefferson Lab, and I think much more broadly, a lot of significant potential in growth in federal research given this asset. This facility has been estimated at about a $300 to $500 million investment in the computing hardware, data center, networking, and the physical plant to support that. This is an artist's rendition of the building on the Jefferson Lab site. What's pictured here is expandable and extensible to meet the needs. This facility lies at the heart of what the US government is calling a data science ecosystem. So the government is thinking through what it would take to construct a basic science research ecosystem that pulls together all of the US Department of Energy basic science facilities. Jefferson Lab's particle accelerator is one of these pictures here. It's this one in the lower left-hand corner, making those facilities and data available to researchers over here on the right, and allowing those researchers to make use of this incredible set of computational infrastructures, from the big supercomputers. Here's the high performance data facility, bringing in simulation and modeling, artificial intelligence tools, digital twins, data repositories, bringing that together to form a broad data science ecosystem, both for basic science and for industry. So what would this mean for Virginia? So HPDF is going to be a real engine for academic and industry research at the cutting edge of computing. It's going to bring research opportunities to Virginia's academic institutions. We're very excited about this. We're very excited about the academic institutions who we're very much engaged with on this topic. Partnerships are already forming. We have a great partnership really coming together with Old Dominion University that I'm very excited about. Excited about some potential developments at William and Mary, and we are reaching out across the Commonwealth. So this is going to be great. This is the kind of facility that our academic community is going to really benefit from by having it right in their backyard. Whether that field is basic research, environmental sciences, coastal resilience, public health, climate change, you name it. This is the sort of facility that supports all of that. It's going to play a significant role in furthering the tech talent pipeline that has been such a key topic for us across the Commonwealth, and our academic institutions are front and center in that. It's going to be a real driver for that. It's going to provide access to a really world unique facility. It's going to attract talent to the Commonwealth. Hopefully this will play a role in stemming some of the tide of difficulties we have in retaining regional talent here in the Hampton Roads and RVA757 area. We want those smart students to stay here and take a job in our universities and our industries and at Jefferson Lab. Going to add a significant asset to the regional ecosystem to further the internet hub concept that we've talked about in RVA 757, and then driving innovation and economic growth by attracting and retaining high-tech and data-focused industries. This is going to be the place for data analytics and data-focused initiatives. The I-64 Innovation Corridor industry clusters, we plug right into directly with 3 of the 4 industry clusters: data centers, digital networking, life sciences and pharmaceuticals for the reasons I mentioned, and national security and cybersecurity, a very interesting opportunity. Closer to home, just right at Jefferson Lab, it's going to double Jefferson Lab's operating budget. It's going to diversify our scientific mission. It's going to open up opportunities that we don't have today as we focus solely on nuclear physics. In the future, we're going to be focusing in other areas and other topics as well across the full breadth of DOE research. So it's going to be an incredible opportunity wherever you're sitting, if you're sitting in the academic world or in industry and innovation, or in a federal facility, it's going to bring a lot to the table. Let me close with how can you help? So first off, many of you have already helped, and I really appreciate that. Thanks so much for the strong support from the business community. DOE's made it clear that they expect co-investment from the state for any significant investments the department is going to make. They can cite this facility at any number of national labs. We want them to cite it at Jefferson Lab. We believe we're the front runner and have a leg up here. And to really cement that, we have been working an initiative in Richmond with a lot of support from the General Assembly and from a number of our delegates and senators in the Hampton Roads region. And that has culminated in budget resolutions in both the House and Senate side and the General Assembly for funding for detailed planning for that building that I showed, for the data center building. So the idea here is to proceed with detailed planning, design the building, and come back to the General Assembly with a significant request for the construction of the shell of a data center building that is ready to be outfitted by the Department of Energy. But the first step there is making sure that this $3 million in budget amendments that match on both the House and Senate side make it through the finish line. This is going to be huge for us. It demonstrates the commitment of the Commonwealth toward making HPDF a reality, and is going to be really important for showing the Commonwealth having skin in the game in this major investment that the department wants to make. So with that, let me bring it to an end, and thank you very much for your attention, and happy to answer some questions.
First of all, Stuart, What an excellent presentation. And I guarantee you, if we were all together in a room, I would want to ask the question, how many of you had no idea this was going on right here in our innovation corridor? And I imagine a number of people would raise their hand. But whether you know a lot or a little, you now know much more. So, well, other thing I would say is that Governor Youngkin is going to be quite an advocate and an ally with the General Assembly on this as well. He's been briefed on this. He's been briefed on, of course, the I-64 expansion. And one of our initiatives, which we're not talking about expressly at this innovation spotlight, but we will in the future, is the global internet hub opportunity we have, where Stuart's project here is a complete and positive match. So with that, Laura, why don't you take over with questions? And even if you did not come up with a question in chat and you'd like to pose one now, we've got just a few minutes for that process. Laura?
Absolutely. So we actually received two questions that are almost there about the exact same topic from Glenn Ballard and Peggy Lane. What impact, if any, does the subsea cables located in Virginia Beach have on Jefferson Lab's current or future capabilities? So how will they work with Jefferson Lab and HPDF?
Yeah, right. I think it all feeds into the ecosystem that we were just talking about in the Internet Hub ecosystem. There are potential opportunities for streaming data from overseas. In some cases, American researchers, are involved in projects overseas that generate a tremendous amount of data. So there is some opportunity there. I would say it's something kind of yet to be fleshed out. The reason I say that is so much of the focus of this facility is, of course, U.S. Department of Energy. So it has a lot to do with moving data around, domestically within the United States. So, I would say a little bit of the homework assignment as we go forward on this is fleshing out those, opportunities and use cases regarding data coming from overseas. But I view it, even without the specific sort of killer app for that, I view it as all of a piece feeding into the ecosystem argument here, that in the region we've got it all: supercomputing, data center, transatlantic landing, internet hub. It's all coming together.
Excellent, thank you. There's one other question. It's from Bill Downey. He asks, Stuart, have you reached out to the universities and their endowment arms for support?
Yes, we've reached out to universities, and like I said, we have some partnerships that are really coming together well that are just great and have gotten a lot of really great support and enthusiasm really across the Commonwealth. You mentioned endowment arms. I would say no, that's not a place we have gone at this point. But one thing I can say is, for a lot of what we're talking about, expansion in data sciences at the individual universities, whether or not explicitly tied to Jefferson Lab's initiative, I think someday will be. And therefore, initiatives underway really across the Commonwealth and growing the data science capability and vision for data sciences are really going to work to strengthen our case and make those partnerships that much stronger. So, we're not in a position where we're, necessarily looking at universities for direct financial support. That's not the sort of type of partnership we're talking about. It's academic partnerships, it's joint faculty that can grow those connections. It's programmatic connections that are so important. And if we get those in place, I think the US government is going to be that much more eager to invest significantly at Jefferson Lab, recognizing that environment that's already in place.
Excellent. Another question has come in from Brian Stevens. He says, how many employees, economic impact for the region, and other than lobbying for the budget amendment, what else can the business community do to support?
The first was how many employees and economic impact. I assume that's from the HPDF. So we currently have 750 employees at the lab. We estimate HPDF is going to require of order 150, and then another, let's say 100 kind of indirect employees. So that's a growth of probably 250 employees at the lab and an increase in operating funds, of order $100 million a year. That's in operation. The project itself would be about $500 million. So these are significant numbers. We've got a little white paper where we've attempted to outline economic impact, but one thing that is always missing from that sort of economic impact is it's very hard to know what the economic impact from the innovation, entrepreneurship, and startup and industry aspects of such an investment are. How many companies are going to start up as a result of this? We know they're going to be there. Very difficult to estimate up front. And if anyone has any ideas on that, I'm all ears.
And one more question from Kasia Grzylkowski. Who is our competition and where do we stand?
Competition would likely be other national labs. If you go back to that diagram, we'll see how that plays out, but it's not uncommon for some sort of site selection process to be carried out. So we want to make sure that we are front and center in that we're the leading candidate, and really important there is going to be how Virginia as an environment for this is situated. So, it's one reason I'm so excited by what's happening in the Commonwealth on tech talent and on data science initiatives and so on.
All right. Well, that's it for the Q&A. I think we have enough time to do a quick wrap up.
Sure, absolutely. Yes, thank you, Laura. Yes, thank you, Laura. Why don't you go back to the slides? I think you've got a what's next slide coming up. Well, if you don't, it doesn't matter. So I want to thank everybody for participating. Remember, you've got an opportunity to take a look at these materials that are on the website. Also, if you didn't participate in last month's Innovation Spotlight, there we spotlighted the pharmaceutical cluster that is growing in RVA expanded Petersburg, and all that is going on there. For those of you that are on the board of directors or Mega Region Institutional Council, our next meeting is March 22nd. And then join us for our next virtual Innovation Spotlight, where we're going to be zeroing in with Glenn Ballard on cybersecurity. You'll see that all of these innovation topics are connected to one another and actually synergistic with one another. So on behalf of Tom Franz, very appreciative of y'all's participation. And at this point, what we would ask is that you follow us. If you have Innovation Spotlight topics, please provide them. If you would like for your association to have an RVA757 Connects briefing, and we are a 501c3 organization, and we rely on funding from the business community and our geography. So we encourage anyone that wishes to participate in funding this collaborative to please be in contact with Laura. So with that, I will call this meeting to a close. Appreciate your participation. Goodbye.